4,000 meters beneath the largest river on Earth, another river flows. It is wider than the Amazon by a factor of 4. It is almost exactly the same length. It has been flowing there always, and we only discovered it in 2011 by accident while analyzing oil well data from the 1970s. In Peru, there is a river that boils, literally, to 96 degrees Celsius, 700 kilometers from the nearest volcano, and science still cannot fully explain why. Beneath the forest canopy, LiDAR technology is revealing thousands of cities that nobody knew existed. And the Amazon itself has only existed for 11 million years. Before that, an inland sea occupied this basin. The Amazon is not a river. It is a planet within a planet, and we have barely begun to read it. Before we go any further, please subscribe to this channel. Your support really helps us to continue our work. Thank you. There is a particular kind of ignorance that is more interesting than knowledge. The ignorance you discover after you thought you already knew everything. The Amazon River has been charted, measured, argued over, and studied for 500 years since European explorers first encountered it in the 16th century. Its length has been debated by geographers for decades. Its biodiversity has been catalogued by thousands of scientists across hundreds of expeditions. Satellite imagery has mapped every bend of its main channel and every major tributary. The Amazon is, by most conventional measures, one of the most studied natural features on the surface of the Earth. And yet, in 2011, a geophysicist named Valia Hamza was analyzing thermal data from 241 wells that the Brazilian oil company Petrobras had drilled across the Amazon basin in the 1970s and 80s. The wells had been drilled to find oil. They did not find much oil. They were largely forgotten in the decades that followed, their data archived and unexamined. Hamza was looking at the thermal signatures of the subsurface, the way heat moved through the rock beneath the Amazon basin, and he noticed something that had no obvious explanation. The thermal patterns suggested a flow of water, not at the surface, not in a shallow aquifer close to the ground, at a depth of approximately 4,000 meters, 13,000 feet, beneath the Amazon River itself. The river that Hamza had discovered, informally named the Hamza River in his honor, is not a river in the conventional sense that the Amazon is a river. It does not flow through an underground cavern, a dramatic subterranean channel carved through limestone, like the famous underground rivers of the Yucatan Peninsula or the caves of Slovenia. It flows through porous sedimentary rock, an aquifer, technically, moving through spaces between rock particles rather than through open water channels. But the distinction matters less than the scale. The Hamza River is approximately 3,700 miles long, almost exactly the length of the Amazon above it. Its width ranges from approximately 200 to 400 kilometers, compared to the Amazon's width of between 1 and 100 kilometers at the surface. In terms of sheer volume occupied, the Hamza dwarfs the Amazon entirely. What the Hamza lacks is speed. The Amazon flows at approximately 5 meters per second in its main channel, a strong, powerful current that has historically drowned men and overturned boats. The Hamza flows at approximately 1 millimeter per second, not per hour, per second. At that rate, a water molecule entering the Hamza at its western end in the Andes foothills would take approximately 30,000 years to reach the Atlantic coast. The Hamza is not a fast river. It is an ancient, slow, subterranean twin, a geological shadow of the river above it, following the same west to east path, carrying the same ultimate destination, operating on timescales that make the Amazon's 11 million years of existence seem brief. The discovery of the Hamza River is, in retrospect, a perfect example of the Amazon's most persistent and most humbling characteristic. The things we do not know about it have a way of being enormous. Not small gaps in knowledge, not minor corrections to an established picture. Enormous, fundamental, river-sized things that were hiding in plain sight in data we already possessed, waiting for someone to ask the right question. The story of how Walia Hamza found the river that bears his name is worth telling in detail, because it illustrates something fundamental about the Amazon: that its greatest secrets are not hidden in remote jungle interiors, accessible only by weeks of difficult travel. They are hidden in plain sight, in data that already existed, in questions that nobody had thought to ask. The Petrobras wells that provided Hamza's data were drilled between the 1970s and 1980s as part of Brazil's national effort to find oil in the Amazon basin. The drilling was expensive, logistically difficult, and largely unsuccessful from a petroleum perspective. The wells were deep, some reaching 4 kilometers into the subsurface, and they were equipped with instruments that measured temperature at various depths as the drill progressed. This thermal data was recorded, archived, and then largely ignored. The oil company was looking for hydrocarbons. It was not looking for rivers. The 241 wells were eventually capped, their data stored in institutional archives, and the geological questions their measurements might have answered were left unasked for decades. What Hamza noticed, when he finally examined the data, was a systematic pattern in the thermal gradients that the wells had recorded. In normal geological conditions, temperature increases with depth at a relatively predictable rate, approximately 30 degrees Celsius per kilometer of depth, modified by the thermal conductivity of the specific rock types encountered. But in the wells drilled in certain parts of the Amazon basin, the thermal gradient was anomalous. The temperature was increasing more slowly than expected at certain depths, which suggested that something was moving through the rock at those depths and carrying heat away. In geology, moving water is one of the most efficient mechanisms for redistributing heat in the subsurface. The pattern Hamza was seeing was the thermal signature of a flow. The mathematics of what Hamza found were staggering when he worked them out. The Hamza River carries approximately 1 million gallons of water per second, 1 million compared to the Amazon's 35 million at the surface. By volume of flow, the Hamza is small compared to the Amazon, but by width, 200 to 400 kilometers compared to the Amazon's 1 to 100 kilometers at the surface. It is enormous. And by length, 3,700 miles, almost exactly matching the Amazon's 3,800 miles, It is the Amazon's precise subterranean twin, following the same west-to-east trajectory, ultimately discharging, scientists believe, into the Atlantic Ocean through the subsurface sediments of the continental shelf, rather than at a visible river mouth. The Hamza is almost certainly not unique. Other major river systems almost certainly have subterranean counterparts flowing through the porous sedimentary rock beneath their basins, fed by the same rainfall that fills the surface rivers, following the same gravitational gradient toward the sea at a fraction of the surface speed. We have not found them because we have not looked. The Amazon was found by accident because the oil industry happened to drill hundreds of deep wells across its basin in the 1970s. Most of the world's great river basins have not been drilled with the same density. The Hamza's existence implies a hidden global network of subterranean water systems that we are only beginning to conceptualize. Valaya Hamza himself said as much in interviews following the discovery. It is possible that underground river systems of a similar kind exist in other parts of the Earth. He was being cautious, as scientists are trained to be. The more honest statement is that they almost certainly do. The physical reality of what it means for water to spend 30,000 years traveling through the Hamza River deserves a moment of contemplation. A raindrop that falls on the eastern slopes of the Peruvian Andes today, falling on the same mountains that reversed the Amazon's direction 11 million years ago, will percolate through the soil, reach the water table, and enter the upper levels of the porous sedimentary rock beneath the basin. From there, it will begin to move eastward, pulled by gravity through the microscopic spaces between rock grains, at a speed of approximately 1 millimeter per second. At that rate, it will take roughly 30,000 years to travel the 3,700 miles to the Atlantic coast. The raindrop that enters the Hamza today will reach the ocean approximately 30,000 years from now, long after any civilization that currently exists on Earth has either transformed itself beyond recognition or ceased to exist. The water in the Hamza River right now fell as rain approximately 30,000 years ago, during the last glacial maximum of the Pleistocene Ice Age, when ice sheets covered much of the northern hemisphere. Sea levels were lower by approximately 120 meters, and anatomically modern humans had only recently arrived in South America. The Hamza is not just a river. It is a time capsule. Andrés Russo had heard about the boiling river as a child, from his grandfather who told stories of the conquistadors finding rivers that boiled in the Amazon. Russo assumed it was legend. When he mentioned it to colleagues as an adult geoscientist, they laughed. A boiling river 700 kilometers from any volcano was physically impossible by standard geological reasoning. Active geothermal systems of that intensity required a volcanic heat source. At 700 kilometers, the thermal energy simply could not be transmitted through the crust without dissipating. The river could not exist. And then Russo's aunt, who had visited the river as a tourist, showed him a photograph. The photograph showed a river running through dense jungle, its surface covered in a continuous veil of steam. The vegetation along its banks bleached and dead, where the hot water and steam had killed it. It was not the photograph of a lukewarm stream that someone had mildly exaggerated. It was a photograph of a river producing steam like a kettle. Russo spent years getting permission to visit the river, which flows through land belonging to the Ashaninka community and had been deliberately kept from outside attention for cultural reasons. When he finally arrived and began taking measurements, the numbers were beyond anything the geological textbooks suggested should be possible. The river, 4 miles long, up to 25 meters wide and 6 meters deep, maintained temperatures between 45 and 96 degrees Celsius along its length. Anything that fell in died. Russo watched frogs fall from overhanging branches into the river and saw them cooking in seconds, their eyes going white as the proteins denatured, the bodies floating downstream in the current. The mechanism Russo eventually proposed, cold water sinking at the edge of the Andes, traveling deep into the crust, being heated by the normal geothermal gradient over kilometers of depth, and then being propelled back to the surface through fault systems under its own thermal pressure, is geologically plausible but remains incompletely documented. The exact pathway of the water, the precise depth at which it achieves its maximum temperature, the specific fault systems through which it rises, these details require geophysical data that has not yet been collected from the remote jungle location of the river. What is known is that the water is geothermally heated, that it is pure enough to drink safely, and that it has been flowing in the same location for long enough that the local people built their entire relationship with the landscape around its presence. The Ashaninka did not need geological instrumentation to understand that this river was different from other rivers. They understood it through 500 years of observation, and they incorporated it into their cosmology long before any scientist arrived with a thermometer. The hidden cities revealed by LiDAR represent a different kind of invisibility, not geological but ecological. The cities were not buried, they were overgrown. The earthworks, causeways, plazas, and residential mounds of the pre-Columbian Amazon civilizations were built from soil. And when those civilizations collapsed after European contact, the jungle reclaimed them within generations. Vines grew over the earthen walls. Trees rooted in the plazas. The causeways connecting settlements became indistinguishable from natural forest ridges. Aerial photography could not see them because the canopy was continuous and opaque. Ground survey could not find them because the forest floor gave no indication of what lay beneath the leaf litter and root systems. For 500 years after the collapse of the civilizations that built them, the cities were as effectively invisible as if they had never existed. LiDAR changed this by doing what no other technology could. It saw through the canopy. The technique works by firing millions of laser pulses from an aircraft at the ground below, measuring the precise time each pulse takes to return. Most pulses hit the canopy and return immediately, mapping the top of the forest. But a small fraction of pulses find gaps in the canopy and reach the ground, returning slightly later. By filtering out the canopy returns and keeping only the ground returns, researchers can construct a precise three-dimensional model of the ground surface beneath the forest, revealing every subtle rise and depression, every earthen wall and ditch, every mound and causeway that the forest has hidden for centuries. What LiDAR has found beneath the Amazon canopy has forced a complete revision of the standard narrative of pre-Columbian South America. The Upano Valley sites in Ecuador, cities and towns covering 300 square kilometers, connected by roads, inhabited for approximately 800 years from 500 BCE to 300 CE, are not the exception. They are one example among dozens of large-scale human landscapes now known from LiDAR surveys across the basin. In the Bolivian Amazon, LiDAR has revealed a network of raised fields, canals, and settlements in the Llanos de Mojos that supported agricultural populations of potentially millions of people. In the Brazilian Amazon, geometric earthworks, circular and rectangular enclosures called geoglyphs, have been found across an area of more than 200,000 square kilometers in the state of Acre, their purpose still debated. In the Peruvian Amazon, terraced hillsides and settlements have been found at elevations previously thought to have been uninhabited. The cumulative picture that is emerging from these surveys is of a pre-Columbian Amazon that was not a wilderness, but a garden, a managed, engineered, densely populated landscape in which the distinction between natural forest and human cultivation was deliberately blurred. The peoples of the Amazon did not live in the forest, as outsiders carefully leaving it undisturbed. They lived as participants in the forest, shaping its composition through selective cultivation of useful species, through the burning that created and maintained the terra preta soils, through the management of floodplain ecosystems for fish and agriculture, through the construction of infrastructure that integrated human settlement into the forest rather than replacing it. The terra preta that these civilizations created is, in this context, not simply an interesting agricultural anomaly. It is the most tangible surviving legacy of a sophisticated civilization's relationship with one of the most challenging agricultural environments on Earth. The problem with farming in the Amazon is not rainfall. Rainfall is abundant. The problem is soil. The laterite soils that underlie most of the Amazon basin are deeply weathered, nutrient-poor, and structurally weak. When the forest is cleared and the nutrients stored in the living biomass are removed, the soil loses productivity within 1 to 3 growing seasons and takes decades to recover, even if left fallow. This is why conventional slash-and-burn agriculture in the Amazon is inherently unstable. It requires constant movement to new forest, clearing new land as each plot is exhausted. Terra Preta solved this problem through a technology whose mechanisms we are still working to understand. The charcoal in Terra Preta was not simply ash. It was produced through a specific process of low oxygen burning that converted organic material into a stable, porous carbon structure that does not decompose. This biochar acts as a physical infrastructure in the soil. Its porous structure holds water and nutrients, and its surface chemistry creates a habitat that specific microbial communities colonize and maintain. The microorganisms in Terra Preta are not random. They are a distinctive community adapted to the biochar environment, and it is apparently their activity that gives terra preta its self-renewing properties. The charcoal itself is essentially permanent. Terra preta deposits contain charcoal that is hundreds or thousands of years old, but that is chemically indistinguishable from recently produced biochar in its functional properties. The microorganisms that inhabit it continue to cycle nutrients, fix nitrogen, and maintain soil fertility for as long as the charcoal structure persists. Modern soil scientists and agricultural researchers are intensely interested in terra preta for obvious reasons. A self-renewing, permanently fertile soil created from organic waste materials and applied to otherwise infertile tropical soils would represent an agricultural revolution in a world where tropical deforestation for agriculture is one of the primary drivers of biodiversity loss and carbon emissions. The fact that pre-Columbian Amazonian peoples solved this problem, apparently solved it completely and sustainably, and that their solution is preserved in the soil of the Amazon, but not in any surviving written record or oral tradition that we have been able to access, is one of the most significant practical losses associated with the collapse of Amazonian civilizations after European contact. We know what they made. We do not know how they made it. The recipe died with the civilization. To understand why this keeps happening, why the Amazon keeps revealing things of staggering magnitude that we should theoretically already know, you need to understand the Amazon not just as a river, but as a geological phenomenon. And that requires going back not 11 million years to the birth of the modern Amazon, but 200 million years to the breaking of Gondwana, and then forward through a geological biography that involves vanished oceans, mountains that reversed a river's flow, and a forest that is simultaneously the oldest and the newest thing on the continent it occupies. 200 million years ago, the landmass that would become South America was part of Gondwana, the southern supercontinent that also included what would become Africa, Antarctica, Australia, and India. The rocks that now form the ancient shields of Brazil and Guyana, the geological foundations of the Amazon basin, some of the oldest exposed rocks on the surface of the Earth, dating back 3 billion years, were fused with the rocks of Western Africa, part of a single continuous Precambrian platform that stretched without interruption across what is now the southern Atlantic Ocean. There was no Amazon. There was no South America. There was only the ancient, stable craton of Gondwana, geologically inert, biologically barren at its surface, containing within its rocks the chemical memory of events that had occurred when the universe was less than half its current age. The breakup of Gondwana, beginning approximately 180 million years ago, was not a single event, but a prolonged geological process driven by the same mantle plume activity that we have discussed in other episodes of this channel. South America and Africa began to separate as a rift opened between them, a rift that would eventually become the South Atlantic Ocean, widening at approximately 2.5 centimeters per year, a rate that over 130 million years has produced an ocean approximately 3,000 kilometers wide at its narrowest point. As South America separated from Africa and moved westward, it carried with it the ancient Precambrian shields that now form the geological backbone of the Amazon basin. And as it moved westward, it was moving toward a collision. In the west, the floor of the Pacific Ocean was moving eastward beneath the advancing South American plate. The collision between the oceanic Pacific plate and the continental South American plate produced the subduction that built the Andes Mountains, the most dramatic geological feature of South America, the second highest mountain range on Earth, and, as it would turn out, the single most important factor in the creation of the Amazon River and the Amazon rainforest. But the Andes did not rise all at once. The Andean uplift was a prolonged process spanning approximately 60 million years, with the most significant period of rapid uplift occurring between 20 and 10 million years ago during the Miocene epoch. And before the Andes reached sufficient height to redirect the drainage of the continent, the western interior of South America was a radically different place from what it is today. Where the rainforest now grows, there was a vast lowland basin, and for tens of millions of years, that lowland basin was not a river. It was a sea. The Pebasian Sea, named after the Pebas Formation, the distinctive sedimentary sequence that preserves its record, occupied a large portion of what is now the western Amazon basin from approximately 23 to 9 million years ago. It was not a true ocean, but it was not a simple lake either. It was a vast, shallow, brackish to freshwater wetland system that at various times was connected to both the Caribbean Sea to the north and possibly to the Pacific Ocean to the west, receiving marine incursions that deposited marine organisms deep into the continental interior. Geologists working in the 1990s were astonished to find the fossilized remains of marine foraminifera, tiny single-celled organisms that live in salt water, in sedimentary deposits hundreds of kilometers from any modern ocean, in the heart of the Peruvian and Colombian Amazon. These were not freshwater organisms. They were marine organisms, preserved in rock in the middle of a continent, testament to a time when the sea reached inland to where the rainforest now stands. The Pebasian system was, by any measure, one of the most extraordinary environments in the history of South America. Its ecology was extraordinary. A massive system of lakes, swamps, rivers, and shallow seas that covered an area larger than the modern Amazon basin, supporting an extraordinarily diverse community of freshwater and brackish water organisms. The Amazon's legendary biodiversity, its status as the most species-rich region on Earth, is not simply the product of its current conditions. It is the accumulated product of geological processes stretching back through the Pebasian wetlands, through the Gondwana breakup, through 30 million years of evolutionary diversification in an environment that was constantly changing, constantly providing new habitats and new barriers that promoted the formation of new species. The Amazon was not born diverse. It became diverse through geological drama. The end of the Pebasian Sea came with the final major pulse of Andean uplift, approximately 9 to 11 million years ago. As the Andes rose, they redirected the drainage of the continent. The rivers that had previously flowed into the Pebasian system from the west now found their way blocked by the rising mountains. The water that had been pooling in the western basin began to find new outlets to the east. And crucially, a sandstone barrier in the eastern Amazon basin that had previously prevented the Pebasian waters from draining eastward, was gradually eroded away, opening a pathway for the accumulated waters of the interior to flow toward the Atlantic Ocean for the first time. The modern Amazon River, the transcontinental river that drains 1/5 of all the fresh water that flows into the world's oceans, is 11 million years old. That sounds ancient by human standards, but is geologically recent. It is younger than our own genus Homo by a factor of approximately 4. The landscape it flows through is ancient. Some of those Precambrian shield rocks are 3 billion years old. But the river itself, in its current west to east transcontinental configuration, is a geological adolescent. And the Amazon's adolescence involved a reversal that is without parallel among the world's great rivers. Before 11 million years ago, the precursors of the Amazon drained westward from the ancient Precambrian shields of Brazil toward the Pacific Ocean. The evidence for this reversal is preserved in tiny zircon crystals, the same extraordinarily durable minerals that we have discussed in the context of early Earth history, found in sediments at the mouth of the Amazon. These zircon crystals carry chemical signatures that indicate they originated in the Andes Mountains of Peru and Ecuador. They could only have reached the mouth of the Amazon on the Atlantic coast by traveling the entire length of the river from west to east. But the Andean source rocks they came from are on the western side of the continent. For those zircons to be at the mouth of the Amazon, the river must have reversed its direction of flow when the Andes rose high enough to redirect the continental drainage. Geologist Russell Mapes made this discovery in 2006, having traveled by plane and boat to collect sediment samples from across the basin. The zircon crystals told a story that the river's surface gave no hint of. This river used to go the other way. The reversal of the Amazon is perhaps the single most dramatic geological event in the recent history of South America, and it had consequences that extend far beyond the hydrology of a single river. The redirection of the Amazon's drainage from west to east fundamentally altered the climate of the entire South American continent. The rising Andes created a rain shadow on their western flank. One of the driest deserts on Earth, the Atacama, sits in the rain shadow of the Andes on the Pacific coast of Chile and Peru. But the eastern slope of the Andes, facing the Amazon basin, receives some of the highest rainfall totals anywhere on Earth. The moisture that evaporates from the Amazon basin travels westward on the trade winds, rises against the Andes, and falls as rain. Rain that then drains eastward into the Amazon, feeding the river, perpetuating the forest, maintaining a hydrological cycle of extraordinary intensity. The Amazon does not simply sit in the rain. In a very real sense, the Amazon makes its own rain. The forest releases approximately 20 billion tons of water vapor into the atmosphere every day through a process called evapotranspiration, the combination of evaporation from water surfaces and transpiration through plant leaves. This water vapor forms what meteorologists and climatologists call atmospheric rivers or flying rivers, vast airborne flows of moisture that travel westward across the continent, delivering rainfall to regions as far away as the pampas of Argentina and the high plateaus of Bolivia. The Amazon is not a passive recipient of South American rainfall. It is an active generator of South American climate, a biological pump of extraordinary power that recycles water through the atmosphere and distributes it across a continent. The scale of this hydrological role is almost impossible to overstate. The Amazon River discharges approximately 209,000 cubic meters of water per second into the Atlantic Ocean, more than the next 7 largest rivers in the world combined. At the river's mouth, the freshwater plume extends hundreds of kilometers into the Atlantic, reducing the ocean's salinity across an area larger than France. The fresh water discharged by the Amazon dilutes the Atlantic Ocean enough to be detectable from satellite, creating a distinctive chemical signature that oceanographers can track for thousands of kilometers from the river's mouth. The Amazon does not end at the Atlantic coast. It reaches into the ocean itself, changing the chemistry of the sea. Beneath the river's extraordinary surface, the Amazon hides physical dimensions that defeat ordinary intuition. The main channel of the Amazon is not a shallow, pastoral watercourse. At its deepest points, near the city of Manaus, where the Rio Negro joins the main channel, the Amazon reaches depths of approximately 90 meters, 300 feet, making it deeper than most of the lakes that most people have ever seen. The average depth of the main channel is approximately 45 meters. The width of the main channel varies from approximately 1 kilometer to 60 kilometers at its widest points during the flood season, when the river expands across its floodplain to cover an area the size of England. During the flood season, the water level in the main channel rises by approximately 15 meters, 50 feet, from its low water level to its high water level. This annual cycle of flooding is not an inconvenience or a disruption. It is the fundamental ecological mechanism of the Amazon floodplain, the driver of the nutrient cycling that supports the extraordinary productivity of the flooded forest. The visibility in the Amazon's waters is, for practical purposes, zero. The main channel carries an enormous load of suspended sediment, the eroded material of the Andes, transported from the highest mountains on the continent to the Atlantic Ocean in a continuous geological conveyor belt. This sediment makes the water the color of pale coffee and limits underwater visibility to centimeters. Below the surface of the Amazon, in the dark, sediment-laden water of its main channel, a world exists that is almost as poorly known to science as the deep ocean floor. The largest freshwater fish on Earth, the arapaima, which can reach lengths of 3 meters and weights of 200 kilograms, cruises through water where divers cannot see their own hands in front of their faces. Electric eels navigate by the electrical fields they generate, because vision is useless in the murk. River dolphins. The pink boto, one of only 5 species of freshwater dolphin in the world, have evolved eyes that are effectively vestigial because the water they inhabit has rendered sight irrelevant. They navigate by echolocation, like bats, sending sonar pulses through the dark water and reading the reflections. The scientific exploration of what lives in the Amazon is a process that has been underway for centuries and remains radically incomplete. In 2022, a single expedition by Conservation International to the Alto Mayo region of the Peruvian Amazon a relatively well-studied area by Amazon standards, catalogued 2,046 species in the course of a single mission. 27 of those species were entirely new to science. Among the newly discovered species was a fish with a globe-shaped head whose purpose scientists still cannot determine. Not understand imperfectly, cannot determine at all. The head is round in a way that no other known fish head is round, and no hypothesis has yet satisfactorily explained what it is for. In the most studied rainforest on Earth, in 2022, scientists found a fish whose basic anatomy they cannot explain. The reason for this persistent incompleteness of knowledge is simple geometry combined with impenetrable ecology. The Amazon basin covers approximately 6.7 million square kilometers, an area larger than the continental United States, excluding Alaska. Of this vast area, the accessible portions, the areas reachable by boat along navigable waterways, represent a fraction. The interior of the Amazon, between river systems, is accessible only on foot through one of the most physically demanding environments on Earth. The forest floor is dark, humid, and navigated by creatures, snakes, insects, parasites that have evolved specifically to inhabit it and that are, individually, poorly studied. The canopy, 60 to 80 meters above the ground, is a completely different environment from the forest floor, with its own community of organisms, many of which have never been observed alive. And between the forest floor and the canopy are multiple intermediate layers, the understory, the mid-story, each with its own ecological character and its own poorly known inhabitants. LiDAR technology, light detection and ranging, the same laser-based remote sensing technique that has transformed archaeology from Mexico to Cambodia, has in the past decade begun to reveal what lies beneath the Amazon canopy that satellite imagery and aerial photography cannot penetrate. The results have been among the most astonishing in the history of Amazonian research. In 2024, archaeologists using LiDAR data identified the oldest known complex Amazonian society in the Upano Valley of eastern Ecuador, a network of cities, towns, and agricultural terraces connected by roads. Inhabited from approximately 500 BCE to approximately 300 CE, covering an area of 300 square kilometers and representing a civilization of potentially tens of thousands of people that was entirely unknown to archaeology until it was seen from above with a laser. The Upano Valley sites predate other known complex Amazonian societies by more than a millennium. The Upano discovery was not unique. LiDAR surveys across the Amazon basin have revealed hundreds of earthworks, causeways, geometric enclosures, and settlement patterns that indicate the Amazon was far more densely populated before European contact than previously believed. The old model of the Amazon as a pristine wilderness, essentially untouched by human modification before Europeans arrived, has been comprehensively dismantled. The Amazon is not a natural forest. It is an anthropogenic landscape, a forest shaped by thousands of years of human management, burning, planting, and engineering. The extraordinary biodiversity of the Amazon is not purely the product of geological processes and evolutionary time. It is partly the product of human selection, human cultivation, and human management carried out across millennia by peoples whose civilizations were then largely destroyed by the diseases that European contact introduced. The most concrete evidence of this ancient human landscape engineering is terra preta, black earth. Across the Amazon basin, scattered among the normal red and yellow laterite soils that characterize the region, are patches of extraordinarily rich, dark, almost black soil that retain their fertility for centuries. Normal Amazonian soil is thin, nutrient-poor, and rapidly exhausted when the forest is cleared. The nutrients that support the forest are stored in the living organisms themselves, rather than in the soil. Terra preta is different. It is deep, up to 2 meters in some locations. It is rich in charcoal, bone fragments, and organic matter. It supports plant growth at rates dramatically higher than the surrounding soil. And it renews itself through the activity of microorganisms that modern soil science still does not fully understand. Terra preta replenishes its own fertility over time, maintaining its productivity even when the forest above it has been removed. Farmers working in the Amazon today still seek out patches of terra preta because the difference in crop yields compared to the surrounding soil is dramatic and immediate. Modern scientists cannot reproduce terra preta. They can identify its components, the charcoal, the bone, the specific microbial communities, but the process by which it was created, maintained, and made self-renewing remains incompletely understood. The people who made it are gone, their civilization destroyed within decades of European contact by smallpox and measles and influenza, to which they had no immunity. What they knew about soil chemistry, about the management of tropical ecosystems, about the creation of self-sustaining agricultural systems in an environment that modern agriculture finds extremely challenging. Most of that knowledge died with them. The boiling river of Peru, Shanay Timpishka in the language of the Ashaninka people who have lived near it for generations, is another expression of the Amazon's capacity to confound. The river was known to the Ashaninka always. They called it the river that was heated by the great serpent Yakumama, the mother of all water, and they used its water for medicinal purposes, believing its purity and heat to be the gift of a powerful spirit. They were right about the purity. The boiling river is remarkably clean to drink. Unlike most Amazon water sources, it does not carry the bacteria and parasites that cause the dysentery and waterborne diseases that have historically made Amazonian water dangerous to consume. The geothermal system that heats it also apparently sterilizes it. What the Ashaninka could not have known, and what Western science did not know until the geologist and National Geographic explorer Andres Russo began studying the river in 2011. The same year that Hamza discovered the underground river is exactly why the water boils. The boiling river is 700 kilometers from the nearest active volcano. In standard geological terms, this means it should not be a geothermal feature. Geothermal hot springs are typically found at or near volcanic activity, where magma close to the surface heats groundwater. At 700 kilometers from any volcano, the conventional explanation for hot springs does not apply. Rousseau's hypothesis, supported by geochemical data and geophysical modeling, is that the boiling river is fed by cold water that sinks deep into the earth at the edge of the Andes, travels downward until it is heated by the normal geothermal gradient of the deep crust, the rate at which temperature increases with depth everywhere on Earth, approximately 30 degrees Celsius per kilometer, and is then propelled back to the surface through geological faults under its own heat and pressure. The water enters cold, travels deep, gets hot, and rises. The 4 miles of boiling river are the surface expression of a water circulation system that extends kilometers into the crust of the Earth. The purity of the water is a consequence of the same deep crustal pathway, filtered through rock for hundreds of years at temperatures that kill everything. The surface of the boiling river reaches temperatures between 45 and 96 degrees Celsius along its 4-mile length. Animals that fall in, frogs, insects, small mammals that stumble at the bank, are killed and cooked within seconds. The river supports its own distinctive ecosystem of heat-tolerant bacteria that form vivid mats of color along the riverbanks, organisms adapted to temperatures that would denature the proteins of every familiar form of life. This is not a metaphor for the Amazon's extremity. It is a literal description of a river that kills on contact, 700 kilometers from the nearest volcano, in a forest where it has been flowing since before any Europeans set foot on the continent. The Amazon exists in a context of almost total scientific incompleteness. The river that flows through 6 million square kilometers of the most biodiverse region on Earth has been studied continuously for 500 years and has yielded, in the past 15 years alone, an underground twin, thousands of hidden cities, a civilization sustaining black soil that modern science cannot replicate, and a boiling river whose heat source took a National Geographic geologist years to partially explain. The species catalogues produced by expeditions to relatively accessible areas of the basin continue to include dozens of organisms entirely unknown to science. The atmospheric rivers that the forest generates carry rainfall across a continent. The geological biography of the basin encompasses 200 million years of continental drift, mountain building, inland seas, and river reversals. The question of why the Amazon cannot truly be explored is, in one sense, a practical question about scale and access. 6.7 million square kilometers is simply too large to examine comprehensively. The canopy is impenetrable to most remote sensing. The water is too dark and too deep to see through. The forest floor is too dense and too dangerous to traverse systematically. But the Amazon resists exploration not because it is remote. It resists because it is not a fixed object. It is a dynamic system, operating across multiple timescales simultaneously. The seconds in which a caiman strikes at prey in the black water, the decades in which the river meanders across its floodplain. The centuries in which the annual flood cycle renews the nutrients of the flooded forest. The millennia in which human civilization shaped the forest and then disappeared into it. The millions of years in which the river reversed its direction and the Andes rose and the Pebasian Sea drained away. The Amazon is all of these things at once. To explore it completely would require not just the ability to be in every place simultaneously, but the ability to observe every moment of 11 million years of geological history, every generation of every species that has ever lived in it, every decision made by every human society that built cities in it and then was erased by disease. What we can do, what the scientists who work in the Amazon are doing with LiDAR and satellite thermal imaging and DNA sequencing and deep well analysis, is read it. Not completely, not definitively, but progressively, layer by layer, revelation by revelation, each new technology opening a window into a dimension of the Amazon that the previous technology could not see. The Hamza River was always there. The boiling water of Chennai Timpishka was always there. The cities of the Upano Valley were always there. The 27 species found in a single expedition in 2022 were always there. What was missing was not the Amazon. What was missing was our capacity to see it. Every river on Earth has a surface and a depth. The Amazon has a surface that dwarfs most other rivers, and a depth, geological, biological, archaeological, hydrological, that makes every other river on Earth look like a feature of the landscape rather than a landscape unto itself. The Pebasian Sea deserves more than a passing mention, because it was not simply a precursor to the Amazon. It was one of the most extraordinary environments in the history of the South American continent. And understanding it changes the way you understand why the Amazon is what it is today. For approximately 14 million years, from 23 to 9 million years ago, the western interior of what is now the Amazon basin was occupied by a vast system of lakes, swamps, and shallow seas collectively called the Pebas system or the Pebasian wetland. At its maximum extent, this system covered an area comparable to the modern Mediterranean Sea. It was not salt water. It was not fresh water. It was something in between. A brackish, chemically complex system that received periodic flooding from both the Caribbean Sea to the north and possibly from the Pacific to the west, creating conditions that were unlike anything that exists on Earth today. Marine foraminifera, single-celled organisms that live exclusively in salt water, have been found fossilized in rocks in the heart of what is now the Peruvian and Colombian Amazon, hundreds of kilometers from any modern ocean. Their presence there is not a geological anomaly to be explained away. It is direct evidence that the sea was here, that where the forest now grows, marine water once covered the land. The Pebasian ecosystem was biologically extraordinary in ways that are directly relevant to the Amazon's modern biodiversity. The system was simultaneously a marine environment, a freshwater environment, and a brackish transitional environment, all existing in proximity, all changing as the connections to the open ocean opened and closed with sea level fluctuations and tectonic shifts. This instability was not destructive. it was generative. Every time the chemistry of the water changed, every time a connection to the Caribbean opened or closed, every time the freshwater input from the Andes increased or decreased, organisms were forced to adapt or perish. The ones that adapted gave rise to lineages that carried their adaptations into the new conditions. The ones that perished left ecological vacuums that were filled by competitors. The result? Over 14 million years of this dynamic instability was an explosion of species diversity that seeded the biological richness of the modern Amazon. The giant river otters of the modern Amazon, the electric eels, the hundreds of species of freshwater fish that exist nowhere else on Earth, the freshwater stingrays that somehow ended up in a river system thousands of kilometers from any ocean. All of these organisms carry in their evolutionary history the signature of the Pebasian world. The Amazon did not become the most biodiverse region on Earth, despite its geological instability. It became the most biodiverse region on Earth because of it. The constant reshuffling of habitats, the repeated isolation and reconnection of populations, the chemical complexity of an environment that was simultaneously river, lake, and sea. These were the engines of speciation that produced the extraordinary biological richness that we are still in the process of cataloging. The numbers are worth dwelling on. The Amazon basin contains approximately 10% of all species on Earth. In terms of plant species alone, the Amazon holds approximately 40,000 species, more than exist in the entire continent of Europe. Bird species, approximately 1,300 compared to Europe's approximately 500. Freshwater fish, approximately 3,000 known species, with estimates of the true total running as high as 5,000. More freshwater fish species than exist in the Atlantic and Pacific Oceans combined. Insects, unknown, but estimates range from the hundreds of thousands to the millions. In a single hectare of Amazon rainforest, an area approximately the size of 2 football fields, there may be more species of insects than exist in all of Great Britain. In a single tree in the Amazon canopy, the biologist Terry Irwin once counted approximately 1,200 species of beetles alone. One tree, 1,200 beetle species. What produces this richness is not simply warmth and rainfall. It is the spatial heterogeneity of a landscape that contains, within 6.7 million square kilometers, an almost infinite variety of microhabitats. Whitewater rivers carrying Andean sediment support entirely different communities from the Blackwater rivers draining the ancient Precambrian shields. The canopy at 60 meters is a different world from the forest floor. Every boundary between environments is an engine of speciation, and the Amazon has more boundaries than any other landscape on Earth. That threshold is not theoretical. It is measurable, and by some estimates we are already approaching it. The water that falls on the Peruvian Andes today will spend 30,000 years traveling through the Hamza River before it reaches the Atlantic. The trees in the flooded forest were shaped by selection pressures that began when the Pebasian Sea was draining away 11 million years ago. The black soil in the clearings of the Brazilian Amazon is the work of hands that have been gone for 500 years. building something so sophisticated that we cannot yet reproduce it. This is what it means to say that the Amazon is not a river. It is not a poetic exaggeration. It is a literal description of an object whose actual nature exceeds the category we assign to it. We called it a river because it has water and a channel and a direction of flow. But it also has an underground twin, a boiling tributary, a hidden ocean in its geological past, a reversed direction that it corrected 11 million years ago, a climate system that it generates rather than merely receives, a civilization it absorbed and then covered with forest, and a biological inventory that remains, after 5 centuries of scientific attention, radically and possibly permanently incomplete. The Amazon is the largest thing on Earth that we do not understand. And the most important thing about that fact is not that it should embarrass us. It is that it should compel us. The Amazon will keep revealing itself. One expedition, one data set, one underground thermal signature at a time, for as long as we are patient and curious enough to keep asking what lies beneath what we already know. Because beneath what we already know, there is always another river. The flying rivers deserve their own moment of attention because they are one of the most counterintuitive and most consequential phenomena in the atmospheric science of the Southern Hemisphere. And they are almost entirely unknown to people who have not specifically studied Amazonian climatology. The flying rivers, those 17 trillion liters of atmospheric moisture cycling westward daily, are not background weather. They are infrastructure, and they depend entirely on the forest that generates them. And it is being dismantled at a rate that has no geological precedent. The Amazon has survived the breakup of Gondwana. It has survived the rise of the Andes and the reversal of its own direction of flow. It has survived the draining of the Pebasian Sea and the ice ages of the Pleistocene that reduced it to a series of forest refugia separated by grasslands, and then expanded it again when the ice retreated. It survived the arrival of human beings approximately 15,000 years ago and the subsequent development of sophisticated agricultural civilizations within it. It survived the catastrophic collapse of those civilizations following European contact, when populations were reduced by as much as 90% within a century by introduced diseases, and the forest reclaimed the cities and fields and terra preta gardens that those civilizations had built. What it may not survive, what is genuinely uncertain in a way that the geological cataclysms of its past were not, is the current rate of deforestation combined with the additional stress of a globally warming climate driven by the same carbon emissions that are warming every other ecosystem on Earth. The Amazon is simultaneously a victim of climate change and one of the most important potential moderators of it. The living trees of the Amazon store approximately 150 to 200 billion tons of carbon in their biomass. If the Amazon were to undergo the dieback scenario, the cascade from rainforest to savanna, a significant fraction of that carbon would be released to the atmosphere as carbon dioxide, accelerating the warming that had triggered the dieback. This is what climate scientists call a positive feedback, a consequence that amplifies its own cause. and it represents one of the most significant tipping points in the Earth's climate system. The Amazon that Valia Hamza discovered a hidden river beneath. The Amazon that Andres Russo found a boiling river within. The Amazon that LiDAR has revealed to be a landscape of hidden cities. The Amazon that contains fish with heads that science cannot explain. This Amazon is not merely a scientific curiosity or a subject for nature documentaries. It is a working part of the planetary system, performing functions that no human technology can replicate, storing carbon that took millions of years to accumulate, maintaining rainfall patterns that feed hundreds of millions of people, and harboring biological diversity that represents the accumulated result of 200 million years of continental drift, geological upheaval, and evolutionary creativity. We are the first civilization in the 11 million year history of the Amazon River to have the technology to read it, to see through its canopy with lasers, to detect its underground twin with thermal analysis of oil well data, to track its flying rivers through satellite atmospheric measurements. We are also the first civilization in that history to have the capacity to destroy it. The two facts are not unrelated. The same industrial civilization that gave us the tools to understand the Amazon is also the civilization whose agricultural expansion, fossil fuel consumption, and political economies are driving the deforestation that threatens it. Stand at the edge of the Amazon River at Manaus, where the black water of the Rio Negro meets the white water of the Solimões. Two rivers that flow side by side for dozens of kilometers without mixing. So different are their chemistry and temperature. A geological signature of the different histories of the watersheds they drain. And you are standing at a place where the visible and the invisible, the understood and the unknown, the ancient and the immediate all converge. Below your feet, 13,000 feet down, the Hamza flows at 1 millimeter per second on its 30,000-year journey to the sea. Above your head, the flying rivers carry 17 trillion liters of water westward through the air. Around you, in the forest within view, there are organisms that science has not yet named. In the soil, there is black earth that human hands made, and that human knowledge cannot yet reproduce. This river has been flowing for 11 million years. It has seen oceans drain and mountains rise and continents separate. It reversed its direction once and may be approaching another reversal, not of its water, but of its ecological state. From the most biodiverse forest in the history of the planet to a savanna that carries no memory of what it replaced. Whether that reversal happens will be determined not by geology, but by choices. Choices being made right now, in the decade in which we live, by governments and corporations and individual consumers, whose decisions collectively determine how much forest remains and how much carbon accumulates in the atmosphere above it. The Amazon cannot truly be explored because it is too large, too deep, too dark, too biologically complex, and too geologically ancient for any human institution or instrument to fully comprehend. But it can be read. And what it is saying In the language of thermal anomalies and boiling springs and atmospheric rivers and hidden cities and self-renewing black soil, is that the world is older and stranger and more interconnected than any map has ever shown, and that the things we have not yet discovered are, as always, the most important ones.